Hello everybody, thanks for joining. Today we're going to be talking about laser plastic welding essentials, innovations, and expert insights. Presenting with me today is Mr. Nick Flesher.
Hello everyone.
He's our Director of Innovation and Development. And I am Jason Dornbos. I am a sales manager at Extol. If you haven't joined an Extol webinar in the past, you should know that we try to keep them very interactive and engaging. So we want you to be live in the chat. There's a few of you that have already started sending messages in the chat. That's great. Keep that up. We want to answer questions as they come up. So if you've got a question, type it in there and we will do our best to address it in the moment. And that way you get your questions answered and the webinar is useful for you. So we're going to start off with a question for you. Why did you sign up for this webinar? I know some of you filled out in the registration form, there was the what do you hope to learn? And we know that people are curious about the fundamentals, the physics behind laser welding, which design guidelines are a must follow, and which industries are commonly using laser welding. There's a bunch of other things that people were hoping to learn, and hopefully we'll address all of that. If by chance we don't answer all of your questions during this hour that we have together, feel free to reach out to us afterwards and we will be following up with you afterwards as well. Anybody in the chat want to say why they signed up for this webinar? Designer, end user of plastic parts, learning particular design rules. Cool. We will get into design. Would like to know more about the process, what the plastics are available and what guidelines are good for design. Yep, we got material stuff in there. Lasers are cool. Thank you, Jeff. Want to reinforce the training I have had. Good. Curious to know what materials lend itself to laser welding process. Good. Okay, another quick question for you. On a scale from 1 to 10, how much experience do you have with laser welding? I'm guessing some of you on the call have never done it, and so you're in the 1 to 2 to 3 range, and then some of you are pretty high up there. 1, 0, 7,
a 0,
a 2.5, a 1. Anybody 10? Because if somebody's a 10, I can maybe unmute you and turn your camera on. You can help us present, right?
I see a couple 7s, and that always makes me nervous. That's but good. We'll collaborate together.
Sweet.
Yeah, it's important just to reemphasize. These are always interactive. Most folks here have probably been to our webinars. Make sure you're asking those questions. We even had CAD dropped into the chat.
Yes.
I don't know that that's probably what most folks would want to do, but
you're welcome to.
You're more than welcome to. We want to make sure this is valuable to all, and most everyone attends a webinar when they actually have a problem to solve.
So we aim to solve those problems.
That's right.
All right. Let's dive in. Laser plastic welding.
Yeah.
Take it away, Nick.
You got it, man. It's a 3-step process, everyone. This is through transmission laser plastic welding. We're going to talk about a variant of laser plastic welding, but it's simply clamping 2 parts together, heating the part with the laser. We're going to talk about what makes the laser heat the plastic shortly, and then there's a cooling period. So what makes a successful weld? We have identified 3 key elements to that. Intimate contact. You need to make sure that the upper part is in contact with the lower part. And the reason for that is the laser, as it goes through that upper component, absorbs into the lower component, heats that lower component up, and then conduction is what actually heats the upper component in 1 micron through transmission laser plastic welding. We find that about 90% of our applications fall into that category. And so material selection has already been mentioned. Excuse me, it's really important to make sure you've got good transmissivity, good absorptivity. Before I go on, drop in the chat if you know what allows for good transmissivity. No, rather, what can be a hindrance to good transmissivity for parts? Maybe just kind of throw that out from a decision point. I already got a question coming in. Awesome. What's the allowable flatness tolerance for the parts in contact with each other? It's a great question. And candidly, plastic never hits dimensions. So we typically will use a lot of force to do that. Our systems, there's various systems out there, but our systems have a progressive force, so we can adjust that force. It's closed loop feedback, and that tolerance can really depend on, to try to answer that question, can really depend on how large that part is, how rigid that part is, how much pressure you can put into it, And so it's a very difficult thing to give an answer to directly. If it's a very small electronic housing and camera housing, we see that quite a lot. You're probably going to want 20 thou, 30 thou flatness. We can accommodate more for larger parts. You could have 100 thou flatness, but the tool and the press is really doing a lot of the work there. So really good question. And then the third thing you have to have before I answer the other questions that have popped in, compatible materials. Any plastic welding technology, we say this in every webinar, it's really important for everyone to know, you have to have compatible materials. We are going to touch on materials at the end. We had a lot of questions pre-webinar that were really good around material and process compatibility. We've got a compatibility chart we'll show, and then it's, of course, on our website. Jason, what are your thoughts?
So the answer to your question, I believe carbon black additive is one thing that prohibits transmissivity. Absolutely.
Yep. However, it actually really helps with the absorptivity. You got to have some level of absorptive content, and carbon black is typically the cheapest.
Fillers are bad.
Fillers are bad. Fillers, inconsistent fillers especially, are bad.
Yeah.
We do find that we get a lot of glass-filled nylons because this is a really clean process, arguably the cleanest process for welding plastic. And so we do get up to 30% glass. Now, what's really key on that is consistency. So we can get through a lot of glass. It doesn't, it's an insulator, but it actually does conduct, it transmits light. So we can use some glass, but when we see maybe a gate that's, the glass doesn't flow through consistently, that can be a challenge. Longer fibers can be a challenge for consistency. So really good answers, everyone. Appreciate that. We're going to show a couple of videos. Jason, I'm going to ask your help there. Mm-hmm. This is the process itself. It might come across a little chunky. Looks like we might have, there we go.
You going?
Yeah, it's a little jumpy.
Okay.
But that's okay. You'll get the point. And you'll see the scanner kind of jumping around. And that's because we're running here about 3,000 millimeters per second. And then this particular application, one of our key strategies at Extol, we have a couple standard machines, but customization is key. We found that we start with an application-specific approach. This particular customer had budget constraints. We hit 2 cavities. We have 7 tools. We have a quick change tooling system that's in less than a minute. So that's what that system was doing. Those were nylon parts unfilled. This system was a full turnkey Extol system. Customer came to us because we could do both. That's really key and important. It's dry cycling. You're going to see it kind of call out 2 different welding applications or machines. This system had 1 operator, and it would weld a part every, I think, 18 or 20 seconds. Whew. One of the key ways we accomplished that was we looked at the application and we said we need 2 lasers at 500 watts apiece to do that work. So we're seeing more and more applications with multiple scanners. And in this case, it was a flat part. We can do multiple scanners on different angles. But in this case, it was because we needed speed. And the system would do 2 laser welds. This is a filter application. I'll just leave it there. And then we were doing 4 leak chest stations and a laser mark. So a couple different examples just to get you thinking around the machine. Folks often want to skip to the machine. It's important that we always start with the application. That full system that you saw started with pre-production parts and process control. So, sorry, I'll let you drive.
No, you can drive.
So we just want to highlight very quickly, when you hear laser welding, that's a pretty broad category. Most of what we do is quasi-simultaneous. That is one laser source. It could be anywhere from 50 watts up to 750 watts. We find that most plastics, you can do degradation when you get above that. You can accomplish quite a lot with scan speed and power, but that's pretty much the most that we put in. And it's tracing apart really, really fast. And that way you're heating that surface up all at one time. Contour welding uses some of the same hardware. I won't get into the specifics of that. It's really useful with larger systems where you would need multiple scanners, and it can be cost effective, although it's kind of slow, to be honest. Masking is really for really small weld ribs, think like 0.5 millimeters. We see it in the medical space quite a bit. And then I just want to touch on simultaneous welding. You might hear this term. We have a great relationship and partnership with a company in Italy called Chamus Elettra, where we service their equipment in North America. That is many individual lasers around the weld rib. And so it's very fast. It can be cost prohibitive. So, and you can also do some pretty complex geometry. So at Extol, if you come to us with your plastic welding challenge, we're going to look at not just laser everything, but one of those tools we may call on is simultaneous laser welding. So probably the most common question we get, I would say, is why choose laser welding?
Why? It sounds like a 6-year-old.
Yeah, a lot of people say, tell me why. A lot of people say, but isn't laser welding expensive? We're going to talk on price in a minute because that's a misnomer that we've really started to vet out. We've even had customers say to us, wow, this system is just slightly above or the same as vibration welding. So we've done a lot at Extol over the years to bring that cost down. But nonetheless, in some cases, it can be a little more costly. And the three key takeaways are it's super clean, it's ultra precise, and it's fast. One of the fastest out there. It can compete with ultrasonics. Sometimes ultrasonics is faster, but if your part's bigger, it's the fastest that there is. From a precision standpoint, we've talked about 0.7, 0.5 millimeter. Typically, our weld ribs are 2 to 3 millimeters. This part that you see in the middle was less than the diameter of a dime. We've even done smaller. And I think our collapse on that was 0.1 millimeters. So that's the level of precision you have in energy into the plastic, which is really tough to do with ultrasonics. Once that plastic gets going, it just wants to go. We have other, hot plate welding can be quite precise, but those are the three benefits that we typically see. We had questions on physics, Jason, and I'm here for it, but I don't know if everyone else is. So I'm just going to quickly highlight what the heck is going on with shooting these invisible rays.
Well, Adrian said that different materials absorb and transmit different wavelengths of light.
That is true. I don't know that I want to go there. Adrian, he or she, you might be able to school us on that. So that is actually true. So it depends on the color, depends on the pigment, depends on the material type. But just to give you a 10-second view, electromagnetic waves go from gamma rays all the way to radio waves. We are dealing in the near IR to short wave IR length. Okay, so
we've zoomed
way in. So that's the whole big thing: visible spectrum, infrared spectrum, and then we are using 2 wavelengths. Different companies might choose different ones. 980 and 1980 for 2 micron, as it's called. I'm going to touch on 2 micron in just a minute.
Okay.
So that's what wavelength we're emitting. There's also power, as I mentioned. To touch on when you might say, what's this 2 micron thing? You might not have heard of that. You may be using it in production right now. 1 micron transmissive kind of looks like that. It's super controlled right at the melt face. You might get literally flash that doesn't even look like flash. It looks like there's just a wetted out line in the plastic. Clear to clear can often use 2 micron. We've also done direct laser. You'll see a slide on that in a minute, where you get more heat affected zone into the plastic. So 1 micron is really precise. 2 micron can do clear to clear. You can actually have the clear absorb at those wavelengths. And then there's direct. Direct, we've used both wavelengths. You're essentially, if you're familiar with hot plate or IR welding, you're heating both parts and you're pushing them together, just like Jason showed, and we'll show a video in just a minute. Here's another visual for that. This particular one on the right was a quite large part, excuse me, and that was 1 micron, and we hit 8 laser sources and scanners to melt both surfaces. So as I've alluded to a little bit already, it applies energy. Direct laser is applying energy to both components to heat both surfaces, and then the tools press the parts together. This is kind of a cool story.
And very inconsistent in the PowerPoint. That's my fault, you know?
No, I'm the technically challenged here. So load, in this case, it was actually 3 components. We're melting both. You are going to see some smoke. It is not part of the through transmission process, but with direct laser, the parts are open to air. So you do get some plastic degradation. We do have to manage that smoke. In this particular case, customers sold it as ultrasonics, and that was a challenge. They were not able to do that because of what's called far field welding. That's another webinar for another day. Any questions before we keep plugging along? I'll keep going, and if you've
been kind of quiet,
been a little quiet, I bet everyone's filling out their brackets.
Yeah,
because of what you said earlier.
Said that.
Or games might have started actually.
No, I think it's noon.
All right, custom example. So around direct laser plastic welding, this was an example we had where the customer, I won't go into too much detail here, but we were using mirrors to redirect that light, that energy into the areas that we wanted to melt so we could weld. We chose 2 micron because it actually was more beneficial. It gave a little more penetration, a little more heat effect. So in this case, it was actually really good. And our tools on this system were very cost effective. We were rotating the parts while we were using the laser. We typically will bend the light, not rotate parts, but this was best in this application for this customer and actually gave them a pretty cost effective while increasing quality type of solution. Let's touch on mirrors for a minute. The part you see to the left is about a 5-inch diameter part. You can kind of see, I was alluding to that really clean weld area. Right this particular solution, I think, was a PMMA to a polycarbonate. And the mirror to the right, I want to talk about because our customer came to us and they said, we're getting really inconsistent welds in the corners. And then we saw a picture of their tool and it just had linear facets. So it's really important if you're going to play with mirrors that you optically engineer it, that you make sure that the laser is going where you want it to go. I have another example of that in a moment. This was a bit of an oblong part, so we had an oval tool that we designed. And that can be done actually quite cost effectively if it works. Those are for more radial applications. So mirrors, sometimes I showed the example of putting the energy kind of up into a part. Those were more tangent, where the laser is coming in from the side. Let's get into some applications. So here's an application that came to us where the customer really didn't want to change their mold. You can kind of see that flash barely peeking out at the corner.
Right there?
That's it right there. And these are really small. I mean, you can literally see the thumbprint of how small these parts were. And we got them through their build. But essentially what they needed to do was put it in a sacrificial rib. So the point of this kind of example is if you need help with that, we're more than happy to do so. Give you the right ratios. You can see how small this was. I think this rib was 0.7 millimeters roughly. It might be smaller than that even. Yeah. Okay. So when I say rib, Jason, you point right there.
This little guy right there.
That little guy right there.
I can even zoom in.
So the part that you saw didn't have that. And so we worked with the customer to sort of develop that. It had some internal components and things. That was, I think, around 100 watts at around 2 seconds of laser on time, maybe even less. We do see the need sometimes for like high-speed automation, which actually I think brings me to...
For you guys on the call, do you have little tiny parts or do you have big parts?
Yeah, that's a good question.
Or medium parts.
Yeah, because size constraints can be a thing for laser plastic welding. So if anyone wants to share that, that'd be great.
Medium.
Medium. All right, medium's good. Ooh, that's quite small.
Half-inch diameter.
Good. Complete interior. All right, medium. So you can accomplish a lot more with multiple scanners and sources. There's costs associated with that. Typically, we see about a 16-inch by 16-inch window. We can do some planar height differences, so 3 dimensions are possible. We've done up to a 1-inch sort of contour around a part. It depends on where it is. Medium's great. A lot of medium, that's really good.
If you have a 3x2 like Natalie, can you do 2 in 1?
You could do 2 in 1. That's one thing. So I want to Great question, Jason. I'm off script. Hope that's okay with everyone. We don't have a script. That was a joke. 3x2, interesting size. Here's how I would say to look at laser plastic welding from a cost standpoint. If your volumes need it, instead of multiple machines, you can pretty cost effectively do a 2-up, a 3-up, a 4-up, etc. with one laser source. And so you can kind of bring your piece price down. And we've even done actually 3-inch by 2-inch parts. I couldn't share the parts in one machine with independent presses for independent process control. That's actually what we prefer. The video you saw at the beginning that had the 2 parts, that was one position. We weld to a position typically. I'll talk about weld modes in a minute. So having the 2 parts with one press, not ideal. They're sharing the same control parameters, but we have effectively done tooling, like say Natalie's trying to weld, 1 million of those a year. You could effectively take a system and make 4 parts weld at one time with pretty minimum cost impact to get that independent process control, if that makes sense.
Oh, and if we had a machine, say we were doing 4-up, each one of them have an independent press, but one laser scanner hitting all 4 parts. In 8 hours, we could do...
I wasn't even listening. I'm going to be honest.
Okay. I think we need AI to answer that question.
Probably 20 seconds of well process time.
For 4 parts.
So you're getting 12 parts a minute.
And somebody help me out with the math. I'm guessing somebody on the call will be able to do the math faster than we can.
So I just want to show this example. It's a great question. I mean, laser welding is quick. It's really way more about your operator load unload. But the good thing at Extol, which you saw, was we can do automated load unload as well.
Is anybody on the call punching that into their calculator? I'm curious to know the answer now.
All right, so this is just a brief video.
Oh, good.
5,600.
There you go.
Perfect. That's pretty high. I mean, look at that.
2 of them.
Sorry, Brian. I think Ken beat you.
5760.
All right, so Jason, would you mind showing this one? So what you're going to see here.
Come on. Turn this. Go.
You're going to see a pilot beam slowly trace. It's not terribly smooth, I'm seeing, but the internet's the internet. So
mute it. Okay, here we go. Slowly.
There we go. So that's kind of you kind of see.
If you want to see it smoother, I'm going to make a quick plug here.
Yeah.
There is a trade show next week in Nashville called the Max Show. We will have our laser welder there, and you will actually be able to see how quickly that laser moves.
Yep.
Oh, did you miss it?
I think they did.
Okay.
You might want to replay it again. So this is 700. You're going to see it. Look at that. Marty's. Boom. It's telling you exactly.
That's how fast.
Yep. So we've seen laser on times in less than a second. What's more typical? I mentioned glass filled nylon. The 2 500-watt systems. That was a laser on time of I think like 9.5 seconds. Okay. So just to give you an idea, if a customer's got a budget constraint, you might have a laser on time of 20 seconds. But you might be making 100,000 parts a year, and that's fine. So we really try to lean into what do you actually need. What was the welding? What was that video welding in free state? Great question. There's actually, so for laser weld tooling, this is in our lab. This is a quick trial. We're using glass to directly clamp the parts. We don't typically do that, but for the visual of this video, we felt like that was appropriate. Oftentimes that slowed down actually worked really well. Yeah. Cool.
Yeah, there's glass clamping on that.
Yeah.
It's not just sitting there.
No. All right, let's talk about a couple of examples. So you might be saying, all right, I'm a product person and I'm trying to think through what the weld design looks like, but at some point, a manufacturing engineer or you are going to have to think about what the manufacturing solution is. This is a system that we created for a customer that had their own internal machine builder. We did all the process control or all the process development, prototype parts, like thousands of prototype parts. And they came to us and said, all right, we want to use a high-speed conveyor. We need to weld 4 parts within a span of, I want to say it was like 5 seconds. I might be off on that, but it was close in that range. It was definitely sub 10 seconds. And we engineered this system. What you'll notice is, and this was kind of the photo to the left is a little bit mid-state. It's not including the adjacent automation. We've had to hide some stuff to protect our customer. But essentially, yeah, we have you'll notice the image in the middle that's got the danger. We engineered a door that would come up and down after every single cycle. I'll tell you, we've seen some integration packages where machine builders should not have been building laser plastic welding systems. They are class 4 lasers that we bring down to class 1 because we're doing risk assessments, we're filing the correct documentation, and making sure that the system is safe. So this particular system had a door installed where you could, the parts were 100% light tight. You can do systems without doors, but in this case, they had space constraints, and so we couldn't do that. We had to use 2 lasers. We had vision in there, and we did all this implementation with a clean runoff so that our customer could have confidence in the process development that we did, have confidence in the system that we sold their machine builder, and this system has been, has been implemented as such.
So draw to the right door. I know the left one is right, but is the right one?
I think so.
Okay.
I think so. Sweet. Yeah. Yeah. So it was so I should say it was a through conveyor, right? So these 2 doors would go up, conveyor would come in, 4 parts presented. It had mirrors that were not attached to the nesting. The scanners could hit the weldable areas, and then we had the vision systems in there looking post-weld to make sure we were good. Because there was no process control from a depth standpoint, we typically use depth as a process control. Another quick application to show another use of mirrors. This is quite subtle. We actually needed to tilt the mirror slightly to get uniformity in the energy. So again, mirrors can be used. It could be cost effective, but it needs to be done correctly. This little system that did this was a benchtop system. Our benchtop system is different than, I haven't found one yet that can do what our benchtop systems can do, which is they're not made necessarily for lab use. This is actually a production solution. This particular one was a lab use case, but we had a 300-watt system in there. I think most of the benchtop systems out there are 50 watts, and they're really made for material compatibility checks. This can do interchangeable tools. It's a great little system. It's a little heavy for benchtop, but is kind of a cost-effective, compact solution for that. All right, I just want to go through this quickly. This is kind of a PCB application. We've got our nanostake, or our InfraStake product staking a PCB, and then you can kind of see a post-weld check. Here's what that weld process looks like.
There you go. Yep.
There you go. And you might be asking yourself, if I can't see the laser, 1 micron you can't see with the eye, how can I see this? It's because we have filters on the camera so you can see what's going on. Okay, so let's talk a little bit of material. We always get questions about material. We're at 30 minutes, so we understand we're kind of getting to the end, so we're picking up the pace some. You can get visually opaque but transmissive to the 1 micron wavelength in certain resin types. This is polycarbonate. This is the same part. We have a laser inspection system where you can see that there are 2 sort of weld areas. So you still get that opaque. You can't really see the weld, but the laser transmits right through it. It's an ultra fast weld. These are just some sample plaques with varying heights, so we can play with different thicknesses and weld times. So know that tool's out there. We can connect you with resin manufacturers who make laser weld specific transmissive plastics. You can check this out on our website. This is, there's a lot of different welding type of material compatibility charts. Most all within a family can be welded. We do have sort of 2 categories there, sort of mid weld expected. In other words, your strength might be 40, 50, 60% parent material. I'm surprised we haven't been asked about how much strength we get. We typically get that. We can pretty easily accomplish 80 to 95% weld strength with laser plastic welding. You really have a low heat affected zone, but you can get that strength really, really high because of how we're heating it while we're applying the pressure, and in a way that the plastic doesn't sort of like break down. If you're looking for more depth, we're going to go into just 3 or 4 screenshots, but download these laser welding design guidelines from our website. A couple of, sorry, got ahead of myself a bit. The transmissive part must be transparent, translucent to IR, but doesn't have to look transparent to the human eye. We kind of gave an example of that a moment ago.
Does the transparent part need to have faces that are normal to the laser, or do you have issues with refraction?
Ooh,
the transparent part
great
has a
question,
more
Justin.
organic shaped outer surface.
Great question. I would say, man, that's a great question.
Pass.
I'm going to phone a friend. I think we get past 30 degrees and we start to have to evaluate it and do some testing, right? You can also do light piping. You can hit kind of we see this in the lighting space, primarily automotive lighting space, where you can kind of follow the contour of the, just like they do in lighting, where you've got an LED that's generating a light in a different spot and it's transmitting it down. So you can do the same kind of thing.
If we're trying to weld down here, trying to get the laser energy to this spot, and this is the outer surface of that transmissive part, we're coming at it like this, whoop, at some angle, right? Some angle, it's going to bounce away.
Yeah.
So the trick is to hit it at the right angle so that it gets down here.
So the question of is normal to the plane important? I would say yes to a point. We can bend the light a little bit and play with those kinds of things. And then there's always again, we try to really be conscious of cost. You can do like a 30 degree, or I've even seen 90 degree parts where you've got multiple scanners hitting multiple parts around it.
About weld strength, if you compare with hot plate welding, do you have higher strength with laser welding? It's not a fair fight.
It's not,
because the weld ribs on a hot plate weld are typically much larger.
Yeah.
But
certainly the case with vibration. Vibe is always, I think, wider than it needs to be. And so parent material strength is not apples to, it might be 2.5 times the wall strength of the part elsewhere if you really need strength.
Laser welding, would you say 80 to 90% parent material strength?
We've seen 95. Yeah. I mean, anyone who says 100% kind of makes me chuckle, because it's breaking in a part that has a stress concentration or is molded different, or whatever the case may be. But I think with confidence we can say we see oftentimes 90%.
And you get about the same with hot plate. It's just often hot plate parts have a wider weld rib. So if you have a vessel and you're welding it together and you have a nice thick weld rib on it, for hot plate, you've got huge burst strengths. For laser welding, if you've got a much smaller, skinnier weld, that's less surface area, it's going to be a lower strength. But if they had apples to apples, the same weld geometry, you'd expect about the same strength.
Yeah. I should throw out the caveat of fillers. If you got talc, if you've got some crummy regrind, if you've got high glass content, you're probably not going to get 95% apples to apples wall strength, kind of material strengths. But I will say I've seen 30% glass filled PA6 where it's breaking everywhere but the weld.
Yeah.
So one might call that 100%. I would call that your design is doing what it's supposed to do, which is you've put stress elsewhere instead of in the weld.
Part size.
Part size. I threw out 16 inch by 16 inch in sort of a standard system. We've done multiple scanners, and it's really sky's the limit. Laser plastic welding for quasi-simultaneous with multiple scanners, you could hit 4 scanners and hit a part 48 inches in length. I've seen simultaneous, or I mentioned simultaneous welding. I've seen 60-inch parts be welded. It's costly, just to be fair. So,
but if you need it, you need it.
Yep. I think I've touched on this a little bit. So, okay. So this is good. I'm sure a lot of folks are like, okay, you've shown me some general weld guidelines, and we got some more coming, but we typically advise to plan for an interference of 0.2 to 1 millimeter in the weld rib. We have welded as much as 1.5, but I'll say with laser welding, that's actually a lot. Because with Vibe, you really have to get the friction going, and then the parts people just hammer the parts. If you have to use laser welding based on those 3 criteria we said, typically we're using 0.7. So you're going to use a little less plastic. It's cleaner because there's actually less of it. Plus, it melts better. So that's what we often see. That we often get, we're engineers, so we're always like, if we throw out these numbers, are people just going to use them? We love to collaborate. We want to talk with you, and our applications team wants to kind of go deep into, okay, but tell me how you're using this, and does it have to be high burst strength or high tensile strength, or is aesthetics matter more to you? So it's tricky to give absolute numbers. We want to work with you on that as much as we can. And I would suggest to the person the person just asked about size limits, come talk to us. What are you dealing with? Maybe laser's not the right thing. Absolute.
Can you manufacture a laser welding machine standalone tailored to our needs?
Absolutely.
That is like our whole thing.
That's the whole thing.
That's our mantra.
That's our whole mantra. I'm going to come back to this because that is the question that we love. Oh man, I'm skipping past all. I bet.
There you go. One more.
Okay, so we have the benchtop I showed. We have this system. Our machines, we can do full turnkey machines, as I showed, with dials, with leak check, with laser marking, actually in the system, right? We find that customers, some of the laser plastic welding folks sort of skimp on power. You got to get enough power. Like once you get to a certain point, you just have to have the power. So we typically will size things up for that, and high press force. We've even used hydraulic systems. So to the question of laser welding machines, this is kind of the array, including the automation system that you saw. We've done multiples of those, very large systems, lights out automation with one operator. Integration packages, as I showed, very small compact systems, benchtop systems, standalones, and then dial systems with quick change tooling to keep your capital costs down while you can do multiple variants with different tools. So as Jason, I like how you said that. It's kind of the thing. Configurable laser plastic welding is where we feel we're different than the rest of the laser plastic welding.
You can get what you need from Extol as opposed to what this is just what we offer. You have to live with it.
Yep. On the interference, assuming the
coming back to that.
Interference needs to be a welder. Jason's just better at point than me.
2 millimeters wide is typical, but you can go narrower or wider.
Yeah. It depends
on how strong you need it to be.
Yeah, 100%. Yeah. If you got a small part and you're like, this thing's not going to see much pressure or more, I just need to seal it. We even see stitch welds. I mean, oftentimes, like I mentioned automotive lighting, but we see that quite a bit, where it doesn't even have to be a hermetic seal. It just needs to be really clean and look like it's almost been molded in. So the weld rib really depends on the use case, and we're happy to talk through that. I would say more than 3 millimeters is a special use case, I would say. I think we've done 4. We also did a spot size laser, which sounds kind of crazy because we used IR and it didn't really work. It was more of a sort of a glue activated. It was kind of a fringe case, but we've got a various different ways to apply that, and I think your welder really depends on that.
It doesn't need to. So you mentioned energy directors on sonic welding. That typically would have a really small initial point of contact to help the vibration propagate. Laser welding does not need that. In fact, you probably don't want that.
We've had ultrasonic designed parts in our lab, and we can make them work with an energy director, but you actually want the heat transfer, and so you want it to be flat. We've done flat to flat. I want to get to the weld joints that I've skipped past. So a simple lap joint. Does anyone see maybe a challenge with that? I'm gonna Jason, what do you think? You essentially are kind of like you're only heating a spot instead of the whole entire weld area.
You're restricting the displacement. You're push these things into each other.
That's the phrase.
Where's it supposed to go?
I'm going to write that down for next time. Restricting displacement. Sacrificial lap joints, inline lap joints. Those are pretty cool. Those are pretty super clean. Simple T joints. You don't have to get complicated, everyone. But if you need it, you can do a sacrificial rib T joint. That sort of allows the flash to kind of poke in it. We find a lot of customers do that because it's simple to mold.
Here, I'm going to zoom in a second.
You want me to go back one?
Actually, no. Shoot, I knew that was going to do. So, okay, you see all these little dark spots on these? That's the overlap. So that's where your lower part is interfering with your upper part. And because we've applied the laser to it, that material has to go somewhere. You can't have two bits of material in the same spot. So all of these, the weld goes in and it goes out. So you're going to get a little bit of flash here and a little bit of flash there. Same thing here, a little flash there, a little flash there. So the idea with these different skirts and different pockets that are designed in to handle the flash is, you know, the material is going to go this way and that way. And so your little skirt can be designed to either hide it or just keep it inside of a certain area. That's what all these are doing.
Yep. All right, I showed some radial examples, application-wise, mirrors, and so on. Sometimes you can spin parts, by the way. We don't love that because we want to go fast. And we find that it's a little bit cheaper to bend, just make the light go where you want to go instead of manipulating the part. And so this is kind of the rough guideline that we give to that. We typically are applying pressure in an upper tool to make sure we've got that intimate contact in these kind of examples. Pretty unique. We've also done radial joints where there isn't an angle like this. It's like a barb. So think of like a hose slipped on a barb where there's sort of inherent interference or pressure. Inherent pressure from the two parts. Just touch on process controls quickly, and that is we essentially have force, laser weld depth, laser weld wattage, how focused is the beam, what's the path, number of passes, laser speed. I would say 90% of the time we weld on collapse, meaning you set how deep you want that weld to go. The machine takes basically a data, says, all right, I've hit a pre-weld position. We actually have settling speed because what we found is some plastics would just kind of continue to collapse. So we wait, make sure we get to a spot we want to actually say, okay, zero the position. Apply the laser energy while it's collapsing. Okay, I've hit 0.5 millimeters. And I'm going back and forth because we have inches on the screen. And then we stop. And then we can actually adjust the force up. So we have approach force, weld force, and hold force. So those are kind of the main parameters. You'll notice alarm limits. We use these. Beware if you're looking at laser welding and doesn't have that, particularly if you're using collapse, all that SPC data is available. And you can see on this particular example, we were hitting a pretty tight 0.008 inches with a 0.005 plus or minus on the approach. Sorry, that was approach limit. Collapse limit was they didn't want to go lower than 0.007. So yep. And then I mentioned the laser settings. We do have a system that works in conjunction with our process screen where we're focusing on power and speed. I've talked about machines a little bit. I had to skip ahead on that because I got excited. Yeah, which should happen. So how do you get to the right solution? Mention costs a number of times. It all depends on your volumes and weld quality and those kinds of things. So we want to work with you on that. We want to make sure you arrive at the right equipment solution after we know we've got the process nailed down. This system was a dial system for operator load, unload, and we had to basically sort of pair. I mentioned it before, and we've done it with countless other examples where we're actually doing two welds in one machine. And then we had quick change tooling on that because the volumes allowed for it. So we try to look at adjacent functions. We've been a custom machine builder for 40 years. And so we can say, all right, you want to do a compression. We've done compression limiters. I've mentioned leak test, laser marking, a variety of different things like that. So, and then the quality parameters. You got to know you're making a good part. So with that.
Yeah. So a quick summary about who Extol is. We're a manufacturing technology company. We help improve how plastic products are made. And as you can see, we specialize in solving tough challenges for plastic product manufacturers like yourself. We believe that the best solutions are tailored to meet the needs of your equipment. That question about can we tailor a laser welder to your needs is so spot on. And we try to do that with not only laser welding, but all of the machines and equipment that we make. That's why we have both plastic welding expertise and custom automation expertise. Our welding skills equip us to solve those tough plastic welding challenges, and our custom automation experience enables us to tailor the equipment to meet your specific needs. So when you work with us, you don't have to choose between a company that has plastic welding or custom automation expertise. We don't make you compromise. You get a configurable plastic welding solution that's optimized for performance. You can see here our service areas. We help manufacturers in 3 main areas with collaborative and consultative engineering services. We have innovative plastic assembly technologies, both welding and staking. We've talked about welding today, but staking is something that we do. And then we have flexible manufacturing equipment. We do have some standard machines to help streamline things, fast turnarounds, and getting those machines to you quickly with what we consider the most common typical settings. And then we have, of course, the ability to customize and make automation around those machines. And then integration. We can, as you saw, we can take a laser welder and make it so that it's integratable into your automation line, whether you have your own team that's going to build the automation or whether you want Extol to do that for you. We can kind of work with you on across many, many different use cases.
2 questions just came up. Jason got through that faster than I've ever read through it. What type of laser are we using? We're using a direct diode. That's kind of the simple answer. It's essentially it's someone here in the U.S. that we use, and they make lasers for the military, so they're a very sturdy supplier. HDP, Adrian, we're gonna have to get back to you on that one. It's a very good deep dive question. HDPE, what type of additives would you want for 1 micron? So we will make sure we follow up with that. That's a good question.
While you are thinking of questions to ask, because I'm going to plug the next webinar. This is happening next month, April 14. We will be talking about InfraStake, the premier IR plastic staking technology, and the 2 presenters are 2 people that know InfraStake better than I know the back of my hand. So
that's saying something.
Yeah, if you have questions about InfraStake, that is the one to join for sure.
I have a question for our audience.
Okay.
Is there anything you would recommend that we could do better? This is a bit spicy. I don't know. See what people say. Anything we could do better on this webinar?
Please don't say better host.
Yeah, not better presenter. Throw that in the chat if you like. Any other questions that we can answer for you before we sign off today? I definitely would say while you're thinking, a little plug, shameless plug for our YouTube channel. We've got a cumulative library of all the webinars on all of our technologies, from IR welding, including our own proprietary InfraGuide technology, our hot plate welding, which we've been told many times by some very impressive companies is one of the best out on the market. Certainly our NanoStake and InfraStake, which are both proprietary technologies. All that information is out there for you, and we love talking about application specific. So hit us up if you've got a part you just don't know how to put together, because maybe laser's not the right thing. Is that the way to close on a laser?
I don't know. Well, there was a question about hot plate, and do we have a planned webinar on hot plate welding? We certainly do. Currently, it's planned for May 14. That's sort of a tentative date, but sometime in May, we will have a webinar about hot plate welding and welding large pallet-sized parts. So stay tuned for that.
Just got a question. Laser etching machines. Post-molded, plus painted, add laser etching for visual patterns. I've had 3 discussions around this. We have not dove. We've not gotten into that space yet. Okay. What we have found was laser cutting, laser etching, laser marking, and laser welding are all pretty different tools. They all might be hammers, but one is a tiny little hammer, one's a sledgehammer. I would put laser plastic welding in the sledgehammer category. We especially have found that when customers come to us and say, I tried laser welding, it wasn't working great. How many watts were you using? 50. We would have started with 300. So the optics are different, the wavelengths are different, and the welds are different. So it's a great question. We do have someone we can send your way, a referral that we've actually gone to their lab and done some experiments and stuff. So you can follow up on that.
If you are in the Nashville area next week, the Max show is at the Music City Center, and you can come to booth 923, see our laser welder in person. And you can also, if you want to come early, come on Tuesday. You can listen to me talk and drone on and on and on about plastic welding. So it'll be a fun time. I promise, try not to keep it boring, and maybe we can get a beer afterwards.
Thanks everyone for your time. We always appreciate it.
Have a good one.